Hey, you doing? I'm Mr. Rose, and today we're going to be talking about forces and potential energy. Basically, how they're related. I just spelled energy wrong. How they're related, and specifically where that little pesky negative sign comes from. So we're going to start real simple because, this negative really gives a lot of people some hangups. So we're going to try and examine where that negative comes from. And actually, if you don't know what we're talking about, stay tuned because you'll figure this out, or we'll figure this out together as we go. So we're going to start nice and simple. I'm going to say there's some kind of a block. And that block is moving on a plane because I apply some force to it. Right? Nothing new here. That force we know is a little vector. I'm going to say that block is moving in that direction. And we're going to say it's moving about the x-axis, make it nice and physicsy. And it's going to move, so we'll go from point A to point B because of this applied force. Now I am going to make this applied force not as straightforward. I'm going to say that applied force is in the x direction, but I'm going to say it varies in the x direction. So when I have f of x and this x in parentheses, this is a variable force about that x direction. So it is moving in our x direction, and we know that if I wanted to find the work done, we already know this. Let's say because of that force, f of x, along that x-axis, I would have to take some derivatives, have to use some calculus. And now this dx, I'm going from A to B, that means I want to sum up all of the force from A to B. So that is my antiderivative. And we know this already. This is just our definition of work. We should also recall that we know that work, by definition, is a change in kinetic energy. Remember that work kinetic energy formula? So my work here in the x direction could just be my change in kinetic energy. So I could really just say that's also 1/2 mvb squared minus va squared. Guess I would need the b there and the a there to be keeping my standard form here. And essentially, this work kinetic energy theorem is pretty much telling us that if an object moves, well, what happens if that object moves? If an object moves, there has to be a change in specifically kinetic energy. And if there's a change in kinetic energy, that must mean work was done. Right? So this was a nice quick review of really what we were talking about last chapter with that work kinetic energy theorem. Now what we're going to add into that is 4 conservative forces. So what if I'm looking at work done and energy done for conservative forces? Well, conservative forces, we should remember what conservative forces are. A conservative force is is when energy can be put 100% back into the object. Example of conservative forces are gravitational, or forces due to gravitational fields. Elastic potential energy is one of the examples that we've worked with. Later on in the year, we're going to talk about electric forces and electric fields. So those are also conservative forces. And this is when I'm not losing, say, energy to the system. Like friction is that non-conservative force. So right now, we're going to examine this with regard to a conservative force. Get some new paper here. So what does that actually mean for us? Oh, making a mess. What does that actually mean for us? Well, required for a conservative force, I know if I have a conservative force, let's say in the x direction, that requirement has to be a change in potential energy about some x. Right? Now this is just my definition. And that negative sign, that's that pesky negative we're talking about. Now with these deltas, this is really not an AP type thing. This is like if I was using an average force. Some average force there, right? We don't want an average force. I want maybe to be examining some instantaneous force. Well, how do I do that? Remember these deltas, that's kind of just our intro. If I want my instantaneous energy or my instantaneous force, I need to take the limit as x approaches 0, or I should say as my change in x approaches 0, which is introducing some calculus. So I would say that f of x along my x-axis is negative du in that x direction over dx. So we're really saying this u, this change in potential energy with respect to x, is how much that energy is going to change with regard to position. Now, just like kinetic energy was moving, its position had to be changing. So this is kind of just an extension of what we were saying before. Well, we know I can rearrange this, and I can end up with something that looks like f of x along that x-axis dx is equal to du, the change in potential, my infinitesimal change, again along that x-axis. When I distributed, I brought that negative to the other side. And now I know if I'm going to move, say, from A to B like I initially defined, if I'm traveling from A to B, that means I need to sum up all of that part. Or take the antiderivative, my macroscopic, right? These du's are microscopic, this microscopic change. Well, this macroscopic change, I'm going to take the antiderivative from A to B of f of x dx, and that's going to be equal to my antiderivative from A to B of du in that x along my x-axis. Well, if I want to say keep that side the same and I can expand that out so I have some formula, I would have the negative AB of my force along the x-axis with regard to x equal to the antiderivative here. It's going to move up a little bit. The antiderivative there is my potential at B minus my potential at A. And that might look kind of vaguely familiar, specifically this half of my formula. So in other words, to sum up, this pretty much says if I have a difference in potential energy, like right here, right? If I have a difference in potential energy right there, that has to be due to the negative work done to move from A to B. What do you mean? It has to be due to the negative work done. How am I pulling that together? Well, we just said work was equal to the object moving from A to B of f of x along my x-axis dx. That was from the previous page. Show that to you right here, right? This is from our previous page. Now, if I combine that to what we just figured out, here my change in potential energy along the x-axis is equal to my negative from A to B of f in that x along the x-axis dx. There is that pesky negative sign. Oh, I'm writing all this stuff down that you can't see. There is that pesky negative sign. So this, the work done, is the force from A to B. My potential energy, or my change in potential energy, is equal to that negative work done, right? That is just my negative work. So that's kind of a big concept for us to deal with. So where are we going with this? Well, we essentially just proved, or just we have just shown that our work done is equal to our negative change in potential energy. Now, I was talking about conservative forces. So if I have a conservative force, we know that those changes have to be equal. So in my calculus form, kind of bring everything together, I've got this negative du in the x direction over dx. And if I was going to talk about, like, this could be any potential energy, the only other type of energy that we've dealt with thus far is that elastic potential energy. So I could say the same thing, negative d dx of our elastic kinetic energy, 1/2 kx squared. And when I take the derivative of that, I would just get that force in the x direction, negative k x. So this is really just applying what we know. Now I know what you're thinking. You're thinking, Mr. Rose, what if there are 3 dimensions? Because we do live in 3 dimensions, those I, j, and k hats. Well, we can do that. We can just extend this into all 3 dimensions. Now it's going to get a little complicated. The x, we would have the same thing in the y. Negative du over dy in the y direction. Or in the z, which we don't do a whole lot, but it works. Negative du over dz along in that z-axis. So this is what we have separately. So we can see, just looking at this my derivatives, my forces, what does this tell me? This can tell me, I should be able to see that if there are big changes, right? If there is say a big force in any direction, I could be talking about the x, I could be talking about the y, I could be talking about the z. So just looking at one of them, if there's a big force, that would entail that energy changes quickly. Well, that means the same thing that, let's say if there was a small force, that's likely to mean what? That energy will change kind of slowly. Energy, and when I say energy, I mean particular to potential energy, but energy changes slowly. Now, this is kind of summed up as we see these derivatives. What this essentially is saying is that, by definition, force is a gradient. That's a new vocabulary word. Of potential energy. And now this gradient is just a different way to say derivative. And now you're thinking to yourself, why would I need a different way to say just a derivative? Why wouldn't I just say force is a derivative of potential energy? And that's a good question. And to answer your question, it's because it's a special kind of derivative. A derivative that we haven't really seen or talked about yet so much. And that derivative is something that's called a partial derivative. And sorry, just trying to get everything on the camera. What exactly is this partial derivative? Why do I need to know about partial derivatives? Well, what do we know about energy? We know that energy is, in fact, a scalar quantity, correct? And if energy is a scalar quantity, what does that mean? That means if my y position changes, that has nothing to do with the energy in the x direction. If my x direction changes, it has nothing to do with my energy in the y or the z direction, which means we have to have a new way to write these derivatives. And a new way to write these derivatives is, in fact, that gradient. It is also what is something that is called a partial derivative. So what is a partial derivative? First of all, partial derivatives are fun because in actual form, my f of x in the x direction is the negative partial derivative of energy with respect to x. Or in the y direction is equal to the partial. So that weird symbol, that almost 2, that's what it looks like. It's kind of like a 2 or a script 2. Same thing in the z direction. That is our symbol for a partial derivative. So I've said partial derivative now a bunch of times. What exactly does that mean? What a partial derivative means is if we are examining any function that has to do with conservative forces, particular to an axis, right? So particular to an axis. And let's just say the x-axis, because that's what we've been talking about. What that means is we are going to treat the other variables, those other variables like y and z, as constants. So we're going to treat those other variables as constants, which means that force function is equal to the negative change in potential energy, but it is the partial derivative with respect to x in the I direction, plus the partial derivative with respect to y in the j hat direction, plus the partial derivative with respect to z, that should be a u, with respect to z in the k hat direction. This, my friends, by definition, is our gradient. And the gradient in nice, concise form is negative this upside down delta, a triangle. That is my gradient times my potential energy. So we can see from everything here that our energy function is, with respect to our variable force, something moving the f and the x direction or the y direction, they only depend, that's what this partial derivative is, with conservative forces, don't forget. That means it only depends on the change in that direction. Again, energy is a scalar quantity. That means that the energy changing in the y only affects the y, doesn't affect those other two things. We'll do one example of this, but we're going to save that for next time, as that's been a little long. Again, we're kind of experimenting with different ways to give some different types of lectures. Please feel free to like, comment, and subscribe. I've been informed that click doesn't mean anything, but if you would like to click on something, have a blast. I hope you have the energy for it, and I will see you next time.